The Sun, a blazing ball of plasma, a celestial furnace that has nourished life on Earth for billions of years. What fuels this cosmic giant? The answer lies in a process called nuclear fusion. Deep within the Sun's core, under unimaginable pressure and heat, hydrogen atoms fuse together. They form helium and release an extraordinary amount of energy. This energy, in the form of light and heat, radiates outwards, bathing our planet in its life-giving glow. Fusion is the very essence of the Sun's existence. It is the driving force behind its radiance and the reason for our existence. For millennia, humans have marveled at the Sun's power, worshipping it as a deity and harnessing its energy for warmth and sustenance. Yet, it is only in the last century that we've begun to understand the science behind this celestial wonder. The process of fusion is elegant in its simplicity and profound in its implications. Imagine two lightweight atoms like hydrogen overcoming their natural repulsion. Under immense pressure and heat, they collide with such force that their nuclei merge. This fusion creates a heavier atom like helium and releases a tremendous amount of energy. This is the fundamental principle that governs the Sun's energy production. For decades, scientists have dreamt of replicating this process on Earth. Imagine harnessing the power of the stars, unlocking a near-limitless source of clean energy. This is the ultimate goal of fusion research, to create a miniature sun on Earth, a technological marvel that could revolutionize our world. Recreating the conditions at the Sun's core here on Earth is no mean feat. It requires temperatures exceeding millions of degrees Celsius, hotter than the Sun's surface. It also requires immense pressures to force the atoms close enough for fusion to occur. Achieving these extreme conditions is the primary challenge in fusion research. Scientists have developed two main approaches to achieving fusion on Earth: magnetic confinement and inertial confinement. Magnetic confinement fusion uses powerful magnetic fields to contain a superheated plasma. This plasma, a swirling soup of charged particles, is where fusion reactions take place. The most common type of magnetic confinement device is called a tokamak, a donut-shaped reactor where the plasma is confined within a magnetic field. Inertial confinement fusion, on the other hand, uses lasers to compress and heat a tiny pellet of fuel. These lasers, some of the most powerful in the world, deliver their energy onto the fuel pellet with incredible precision. This rapid heating and compression create the extreme conditions needed for fusion to occur. Both approaches have their advantages and challenges. Magnetic confinement offers better confinement times, allowing the plasma to react for longer periods. However, maintaining the stability of the plasma within the magnetic field is a complex task. Inertial confinement, while offering higher energy densities, requires incredibly precise and powerful lasers. Despite significant progress, fusion power still faces significant hurdles. One of the main challenges is achieving a sustained reaction where the energy output exceeds the energy input. This is known as ignition, the holy grail of fusion research. While we've come tantalizingly close, achieving ignition remains elusive. Another challenge is the development of materials that can withstand the extreme conditions inside a fusion reactor. The intense heat and neutron radiation can damage the reactor walls, limiting their lifespan. Scientists are constantly researching new materials and designs to overcome these limitations. The sheer scale and complexity of fusion experiments also pose significant engineering challenges. Building and operating these massive machines requires cutting-edge technology and expertise from various fields, including plasma physics, materials science, and computer engineering. The timeline for achieving commercial fusion power remains uncertain. While some experts are optimistic about breakthroughs in the coming decades, others believe it could take longer. The journey towards fusion energy is fraught with complexities, but the potential rewards are too great to ignore. Section 4. The Promise of Fusion, a World of Benefits. The pursuit of fusion power is driven by its immense potential to revolutionize energy production and address climate change. Unlike fossil fuels, fusion produces no greenhouse gases, offering a clean and sustainable energy source for a brighter future. Fusion reactors produce no long-lived radioactive waste, unlike fission reactors. This eliminates the problem of storing hazardous materials for thousands of years. The byproducts of fusion reactions are primarily helium, an inert and valuable gas. Fusion power plants would be inherently safe. There's no risk of a meltdown like in a fission reactor, as the fusion reaction can be easily stopped. This makes fusion a very attractive option for future energy production. Furthermore, the fuel for fusion is abundant and readily available. Deuterium, a heavy isotope of hydrogen, can be extracted from seawater, providing a virtually inexhaustible energy source. This makes fusion a truly global solution to our energy needs. Section 5. Investing in the future, the economics of fusion. The development of fusion power is a global endeavor, with billions of dollars invested in research and development worldwide. Governments and private companies are increasingly recognizing the potential of this game-changing technology and are pouring resources into its development. The economic benefits of fusion power are significant. A successful fusion industry would create countless jobs and stimulate economic growth. It would also reduce our reliance on fossil fuels, leading to greater energy independence and security. The cost of fusion power is currently a major barrier to its widespread adoption. Building and operating these complex machines is an expensive undertaking. However, as research progresses and technological advancements are made, the cost of fusion energy is expected to decrease significantly. Several private companies are at the forefront of fusion technology, developing innovative approaches and pushing the boundaries of what's possible. These companies, backed by venture capitalists and visionary entrepreneurs, are confident that fusion power will be a commercial reality within our lifetimes. Section 6. Fusion's Dawn, a new era of energy. The quest for fusion power is a testament to human ingenuity and our relentless pursuit of scientific breakthroughs. It is a journey driven by the desire a future powered by the very forces that illuminate the cosmos. While challenges remain, the progress made in recent years has been remarkable. From record-breaking plasma temperatures to advancements in reactor design, closer to the dream of harnessing fusion power. The urgency of developing fusion technology cannot be overstated. Climate change is a pressing global challenge, and we need clean, sustainable energy sources to mitigate impact. Fusion power offers a beacon of hope, a potential solution to one of humanity's greatest challenges. The dawn of fusion power is on the horizon. It promises a future where energy is abundant, clean, all. As we continue to unlock the secrets of the stars, we move closer to realizing this extraordinary potential and ushering in a new era of energy for humankind.